Hello, Joyce.
Yes, sir, you're audible.
Are we going to start soon, or how is that?
Yes, sir, we can start now. So the first presenters in the offline, that would be Aikya Banerjee and Priyajit Jana from ISER, Kolkata. They would be presenting on the influence of sun in secondary cosmic wave flux.
So, am I audible?
Yes, you are audible.
And the screen is visible, right?
It's perfectly visible.
Okay, thank you. So, hello everyone. Good afternoon. Welcome to our work, influence of cosmic sun. Is influence of sun in secondary cosmic ray flux. So, at first, we'd like to thank Physics Society of St. Stephen College, University of Delhi, to deliver our work in front of you. Me and my friend Oiko Banerjee will present our work today, and we both are from Indian Institute of Science, Education and Research, Kolkata. So, let us start with our introduction. As everyone knows that cosmic ray is coming to Earth in every second, but we made the statement. But here a question may arise that what is cosmic ray and what are the possible sources of cosmic ray? So basically, we still don't know the actual source of cosmic ray, but we have identified some possible sources of cosmic ray. Nearest star, sun, that is glowing in our sky. And so to see whether the sun is the major source of cosmic ray or not, or up to that is cosmic ray flux that is coming towards the earth should increase, and during the solar eclipse the rate should decrease because a huge mass passes through. And also if there is some impact, then the question is how much. We have compared the data of these two days with the normal days and find out the coefficient of variation, and we will come back to the result in later. So now let us discuss what is the muon flux on Earth. Cosmic rays are nothing but the full of high energy photons, hydrogen atoms, or all other excited molecules or electrons or and many things. So after entering in the Earth atmosphere, cosmic ray collide with the nuclei present in our Earth atmosphere, and in this collision, many particles fundamental particles created like baryons, baryons, mesons particle, for example, pions, kaons, and we call this particle as a primary cosmic ray particles. So, and since the half-life of this baryons and mesons are very less, and so these particles immediately decay into the secondary cosmic ray particles like electron, muon, and gamma ray, and the decay of process of pions and kaons are given in the equation below, as you can see from the slide. So we call the whole process as a cosmic ray air showers that placed on the Earth, upper Earth atmosphere. Now, as you can see that in this whole process, we are getting a huge amount of muon, and this muon start to fall towards Earth. And now again, here a question may arise that the lifetime of the muon is 2.7 microsecond, and the speed of the muon is close to speed of light. Then how the amount of muon is abundant in the sea level? Because if we consider the special theory of relativity, we can easily explain this result. So now during our summer intensive at Miranda House, New Delhi, we gathered from the detector data available in a QuarkNet site by Fermilab. We are very much thankful to Miranda House, New Delhi and Fermilab for that. Now I would like to request my friend Oiko to take over the discussion.
Thank you, Priyajit, for this introduction. So let us come to the main part, that is the experiment that we have performed. The first part is basically based on the solar eclipse. So for that, we have taken a major solar eclipse happened on 21st of August 2017. Now here a question may arise that why we have taken the solar eclipse that happened on 21st of August 2017. The main reason for that is it's a major solar eclipse that basically happened on a vast region of USA and Canada. And the most of the Fermi-Lab detectors under the CoORDinate project are situated in this region. So basically, it was helpful for us to take the data. We have also gathered few other data from few discrete places in other parts of the globe, but those were very much discrete, and we cannot gather a whole statistical data from that. We have taken this data. Basically, also here we can vary the extent of solar eclipse and also the amount of increase or decrease or whatever that is happening during this in the solar cosmic ray flux during the solar eclipse. So for that, we have taken this data as our major source of, as a major point of our study. And here the major mostly affected regions of US were given. It's Oregon, Idaho, and other states that I have mentioned here. So basically, we have studied this, along with we have studied a few weather studies and other studies, performance and other studies. Basically, why we have taken these other studies, I will come to that after a certain extent. So when we have taken the data, we got the following data pattern. Basically, 4 things were taken from Illinois state, and for all of them, the variation are within 2%, max to max 2.71%, and almost this coefficient of variation is not that much. Like we have taken mostly from Illinois because the maximum solar eclipse was 100, the sun was entirely covered in this region. So therefore, we have taken most of the data from Illinois state. Also, we have taken few other data from other states, and these are the other data sets. Mostly all of them, in all of them, we can see the coefficient of variation is within 2 to 3%. Basically, it is not that much. If we consider that it's all in almost all of them except the Syracuse University. So basically, we can also say that the 3 sigma limit, considering the 3 sigma limit, that is within also 5 to 7% from the mean line. So basically, in all of the data, most of the variation are bound within the 5 to 7% region, except the Syracuse University. For Syracuse University, this value is 4.72%. So we were a bit perplexed about the situation, like this was a point of doubt. And for that, we have studied few other studies. I was mentioning about the humidity, the other parameters. Those are local parameters. Those are humidity, cloud, and other issues. So how they can interact. My dear friend Priyojit explained few moments ago that the solar part, the cosmic rays, actually the secondary particles or the primary particles interact with the nuclei present in the atmosphere. So basically, if some component, if the component of the atmosphere some way changes a little bit, then that should impact in the data. So therefore, the coefficient of variation is, we can exclude this data because there is other change in local parameter, because on the same day, the humidity and other issues were very much high in this place. So basically, we can conclude that mostly the influence of solar eclipse is within 5 to 7%. Now, we got a limit from here that the impact of sun is not that much. If it is that much, then when the moon passes by, then the effect will be more. So basically, the impact of sun is not that much, and it's within 5 to 7%. But here a point may arise. During the solar flare, there are many things happening, like solar flare. When the solar flares happen due to the coronal mass ejection and all other things, solar particle events also happens. Therefore, the particles are accelerated much, and hence we can think that there may be some break in this limit. This limit may break in this point. So is it happening or is it not? So for that, we have studied solar flares. So before going into details about the study regarding solar flares, let us discuss about what is solar flare. Here is just a picture of solar flare is given. Simulation animation is given. Solar flares is intense electromagnetic radiation and sudden explosion of energy in sun's atmosphere due to reconnection of magnetic field. Flares occurs from active regions of the sun which are associated with the sunspot. So due to this magnetic reconnection, the magnetic energy is converted into kinetic energy of the particles, and charged particles are ejected out of the solar outer regions. So solar flares occur when this charged particle interacts with the plasma medium. During solar flares, the solar particle events happen and sun releases a huge amount of charged particle, mostly the protons. So basically, when the huge amount of proton comes out and it is accelerated, it is a high kinetic energy. Therefore, we can think that their energy is much. If the energy is less, then due to the Earth's magnetic field, these particles may not come here. But here I will also come to this point of Earth's magnetic field a few moments later. So basically the energy is much, so we can actually measure some changes in the flux. So how the changes are coming, we have studied solar flares over different different solar flares across last few years, and also we have studied we have taken two major solar flares for the study, and we are going to describe them only because the time constraint is there. So here the first is from 1st September 2017 to 10th October, between which the red mark region is basically the region where the solar flares is happening. And this is a date of solar flare, that is the actual date of solar flares. And then after 2 to 3 days, there is a high increase. I mean, there is an increase in the flux. So basically all of them, in all of the following, there are increase in the cosmic ray flux. Somewhere it is much, somewhere it is less. We have also taken another solar flare happened between 16th of October and 16th of November. It's a 1 month study. And here also we can see it is consistently happening that during or afterwards the solar flare, there is a prominent peak in the data. So we can say that the theoretically assumption that from the theoretical point of view, what we are saying that there may be some increase in the solar cosmic ray flux that may have happened, and that can have happened during this situation. So how can I be so sure that the increase in, I mean, there are a lot of peaks here. So how we are so sure that this is happening due to this? Basically, we have studied almost 10 to 15 different solar flares, and in all of them, it is consistently appearing there is a relative increase in the flux data. So therefore, we are sure that this is happening. So basically, we have studied different thing. We are saying that the Earth's magnetic field is protecting us from the Earth's magnetic field is a retarding force for this cosmic rays. So how? We have taken a major component. There is a horizontal component of Earth's magnetic field and percentage rise. Percentage rise is basically the increase from the lower end of the peak to the higher end. We have taken that way. And we can see that there is a strong negative correlation in both of the data on 28th of October and 10th of September. So basically, both of them suggest that with the increase in horizontal component of Earth's magnetic field, there is a relative decrease in rise. So basically, why this is happening? We have why there is a negative correlation between increase in flux due to solar flares and horizontal component of Earth's magnetic field. Basically, we can say the charge of Muon is 1.6 into 10 to the power minus 19 coulomb, and horizontal magnetic field is perpendicular to the direction of the Earth's to the direction of the velocity. I mean, therefore, we can say there is a force and which is acting this way. So basically, it's a right-hand screw rule. But if we take the charge of the Muon, then it will be directed this way, and therefore there is a deflection force. So basically, Earth is deflecting the particles and keeping us safe from this cosmic rays. So will it the same happen in polar regions? Basically, I guess not, because there is a magnetic dip in the solar polar regions is 90% and 90 degree, and hence we can say that the particles will show some different kind of pattern. But due to the unavailability of detectors in or around the polar regions, no perfect measurement was done, and we think this is a drawback of our study, and we need further studies needed in this region, in this aspect. Now I will ask Priyojit to make the concluding remarks.
Thanks, Soiko, for your nice explanation. So from our first experiment, we can conclude that the effect of sun on cosmic ray flux is 5 to 7%. And from the second experiment, we found that the solar flares rate Muon flux that is coming on Earth increases, but it is very less, and also the relative increase in Muon flux shows strongly negative correlation with the Earth horizontal magnetic field. So thank you. This now, if you have any question, all are welcome.
Okay. Hello.
Yes.
Yeah. Again, Priyajit, thank you for the presentation. So I have few questions to you, guys. So first of all, tell me, were you in Delhi to take the observation? You visited Miranda House?
Sir, we are actually we are doing the summer internship in Miranda House, and Miranda House, the project we are doing is under CoopNet by Fermilab. So we got a study. I mean, Fermilab actually provides us the data.
Was it online or offline?
Yes, it was online, sir. It was in the last summer to 2020.
So yeah. So are you aware about what kind of detectors are they using for collecting the data for for collecting the cosmic rays?
So I will ask Priyojit about it. He can mention. So about the detectors.
Cosmic ray detector, the detector that you must be using for collecting the data.
We don't have that much information about the detector, but this
Miranda have this detector.
Miranda House have the detectors since this was online intensive. So, we have not that much information about the detector.
This was basically
is it
scintillators and particle detectors like.
Yeah, particle detector. Was it a GM counter or a scintillator? What kind of any?
It is a scintillator based.
Okay, it was scintillator. Okay, so second thing, you were talking about the coronal mass ejection. So in the coronal mass ejection, you might have heard about the magnetic reconnections. So what do you understand from magnetic reconnection? What is the meaning of what do happen to the magnetic field in the magnetic reconnection?
So can you say again?
So my question is, what do you understand from the magnetic reconnection?
So basically, sir, it's like what we have understand from our perspective is like during this is a normal solar cycle. I mean, in sun there is a normal solar cycle happening, and due to some cases in the sun, I mean, in some there are some bright spot, and there are some magnetic. I mean, what we understood is like the magnetic field is sometime due to this event, the magnetic field is converted into kinetic energy of the. And these particles are actually accelerated by that. So basically, from our perspective, we know that much.
Okay, so you are talking about the plasma confinement in
yes,
magnetic. Okay, good. So last thing, can you just again tell me what are you saying? How much contribution of cosmic rays sun is going to have?
So from the data, if we consider the 3 sigma limit, I mean, almost we can know about from Gaussian. This is almost this contains the entire thing. If we even consider the 3 sigma limit, it is within 5 to 7%. So basically, if sun is contributing, it is very less. Okay. So still, that is why we have mentioned in the beginning that we still don't know the actual source. Like sun is not the major source.
Okay. Other than muons, which cosmic particle we can easily detect on Earth?
Any comment?
Muons you have already discussed about that muons.
Yes,
see. Other particles? Because cosmic ray will include heavy ions, electrons, protons, everything. Muons and large chunk of particles.
Can you say it's like, can it be kaons or?
No, I don't think kaons or baryons or meson particle can be like detect from in the sea level because their lifetime is very much less. So
muon can be detected facts. That is also evident from.
But and if we try with the electron, but electron is, I mean, in our Earth also electron is more abundant. So like, we cannot base on we can't say on the base of electron, I guess.
Okay. And Rajit, thank you.
All right. So have they left? Akya? Are you people there?
Yes, we are there.
Okay. So tell me, you are talking about scintillation detector. What other detectors? What other detectors are there to detect cosmic rays?
So can you say again once?
I'm saying you are saying that scintillation detectors are used for collecting the data in your study. So what other types of detectors are there?
So we have studied this about scintillator detection, and during our in summer internship we have studied this only. So we actually. Okay.
Please switch on your video.
Yes, we can. Are we visible now?
Yeah, now you are visible.
We know about this detector. Like there is a, I mean, how this detector works. We know about, but we don't know about other details. Like in Fermilab, we have studied about 2 type of detectors. Right. One is this kind of detector using scintillator, and another one. Please, can you remember the name?
I can see CMS lab.
CMS lab. That was another part.
So we have not explored the CMS.
We have not experienced about the CMS.
All right. And you are talking about baryons and mesons. Can you tell me some characteristics of these particles?
So mesons are basically like it's not one quark and one anti-quark, and the baryons are like consist of three quarks.
Okay.
Uh,
What else? What kind of interaction?
so what kinds of interaction? Basically, it can basically, since quarks are included, so basically it can go through all four kind of fundamental interaction. Uh, like for electromagnetic interaction, strong interaction, or weak interaction, everything.
Okay. All right.
Yeah.
Means high altitude region.
So basically, we have we also mentioned, I mean, a few aspects about polar regions. We did not get enough chance to detect, like when the cosmic ray, I mean, particles are coming through these polar regions, the Earth's magnetic field is completely, I mean, it's not the same as the that is throughout the Earth. Like the magnetic dip is different, and also therefore the particles form some helical motion, and they due to that they interact with the atmosphere and form some ionization, and hence we can say there is a luminescence in the sky and also basically this luminescence is visible because almost 6 months, I mean, for 6 months there is a complete night in that region. So this is more prominently visible due to that because there is no sun that time. So that is also there.
Okay. Yeah. Okay. Thanks.
Is Harsh there?
Yes, sir. Just
Hello, am I audible?
Yes, you are audible.
Yeah. So you talk about solar radiation. So most of the solar radiation is just positive and not negative. So what is the reason behind this?
Can you just say again?
Most of the space radiation and particularly solar radiation is just positive and not the negative. What is the reason behind this?
Positive. I mean, I cannot follow you properly.
So whenever space radiation came, na, it is just positively charged. It is not negatively charged. So why
Okay.
not it just positively charged?
Therefore, we can say like the things are coming from plasma, and in plasma state, the electrons are completely out of. I mean, this is a high energy. I mean, the temperature is very high, and in plasma state, we know that the electrons are out of it. So basically, maybe that is a reason. Yeah, all are in ionization.
Where electrons gone?
Huh? What?
Where the electrons gone? Because it is basically the particles, alpha particles. So when alpha particles made, then somewhere electrons have to go, na. So where electrons gone, and when it is decimated.
We don't know much about that. Pujit, can you comment about it?
Maybe it's in atmosphere or like
Yeah,
few
maybe.
electrons.
Maybe.
I don't know. Like we don't know.
Okay. They actually decimated in the quantum is getting. When alpha particle came, then quantum is getting case base, and they. Okay, fine.
Do we have any other questions? Well, then, thank you very much, IK Banerjee and Priyajit Jana. We'll be moving
Yes.
on to the next presentation. For the next presentation, we have Maitreya Bhattacharjee, who is from IACS Kolkata, and the presentation is on the topic of the trimeter of graphs. So, Maitreya, you can take over.
Yeah. So, am I audible?
Yes, you are.
Audible and visible?
Yes. Yeah.
Okay, I'm just sharing my screen. Yeah, so are my slides visible? Hello?
Yes, yes.
Yes, they're visible, Maitra.
Yes. Okay. Let's start. Yeah. So first of all, thanks a lot to the organizers for giving me this wonderful opportunity. I'm Moitro Bhattacharjee. I am a sophomore at ICS Kolkata. And today I will be reporting on some recent work which I've been doing with Professor Angshuman Das from Presidency University. So here is a brief.
Just 1 second. Maitru, what is your background? Mathematics or physics?
I am a BSMS student and I am majoring in mathematics currently.
Okay.
Yeah.
Thank you.
Yeah. So here is a brief overview of the talk. I will introduce the notion of a graph and some related terminologies. Then I will talk about the very new parameter trimeter on which I have been working. Then discuss some very new theorems, some upper bounds and some lower bounds, basically some inequalities. And I will also discuss the brief idea behind the proof of them. And then I will discuss something very interesting, mainly the illustration of the numerical values of this particular trimeter for various families of graphs, and then finally end by stating some open problems and conclusions. So here are the main references for the talk. This is the main paper on which the concept emerged, and this is the following paper on this. And this work is also based on some of my summer internship work at Presidency and another expository article which I published in this magazine published by St. Xavier's College, Kolkata. Okay, so let's begin. So here is the basic structure of a graph, as you all can see. So the circles present over here is known as vertices, and the straight lines connecting them are known as the edges. And this was introduced by the famous mathematician Leonhard Euler. And today they are extensively used in many domains like mathematics, physics as well, statistics, computer science, definitely, discrete mathematics, etc. and etc. And so mainly whatever graphs we will consider in our talk will be simple. They will be finite. Finite meaning the number of vertices will be finite. Undirected meaning the edges will not point towards any particular vertex and they will be connected. Meaning that starting from any vertex in the graph, you can visit to any other vertex with the means of the edges. And another terminology is that the graphs may or may not contain cycles. A cycles in a graph is defined as this kind of closed loop consisting of vertices and edges. So these are the main concepts. And another, so these are the terminologies associated with a graph. The distance defined between two particular vertices x and y is the shortest number of edges joining the two vertices. This is how we count the distance in a graph. And the eccentricity is defined as follows: maximum of this particular set, and the radius and the diameter. And as we have a concept from our geometry classes, the diameter of a graph is greater than the radius of them, as you can easily see from this definition. So this was the previous work. And another very important concept which I want to introduce is the concept of complementary graph. So as you can see from this particular picture, the vertex set of a graph and its complement remains the same, but the edge set becomes just the complement. The edges which are present in the original graph vanish in the complementary graph. And if we superimpose them, we get the complete graph. That means all possible vertices and all possible edges are connected. Yeah. So let me now move on to the main quantity which we will study in this talk. So this is the definition of the trimeter. It is just defined as the maximum of distance of these three particular vertices where u, v, and w belong to the graph. And yeah, so and as you can guess from the name trimeter, it involves three particular quantities. And the main motivation behind this particular quantity was originated from this paper of Shaha and Panigrahi, which I have quoted over here. And for a very basic example, you can consider a triangle. Then any possible distance between two vertices is 1. So the max, so all the values of this set will be 3. And so the trimeter will of course be 3. Yeah. So let us now consider some inequalities of the trimeter. My first claim is that the trimeter is sandwiched between 3 times the diameter and 2 times the diameter. Yeah. And the proof sketch goes as follows. The upper bound is trivial. The upper bound can be found by just putting the diameter in place of the definition of the trimeter, and it just follows. And for the lower bound, for this term, 2 into diameter less than trimeter, we will have to use something known as the triangle inequality for graphs, in which we will take two particular vertices, A and B, and another vertex which does not belong to A or B, and apply the triangle inequality, as you can see, and then we can arrive in this result. Now let us see the relation of trimeter with radius. So as we can see, and we can guess as well. So as the diameter and diameter and radius are related by this particular fundamental relation. So if using this and the previous result, we can easily arrive in a result which relates the trimeter and the radius. So the trimeter is sandwiched between 2 times the radius and 6 times the radius. And of course, all the graphs we are considering here over here is connected. And the main reason behind that is that if we take a disconnected graph, then the distance between the vertex which is disconnected to the all other vertices is infinity. So things become quite difficult. And so we are considering only connected graph. Yeah. And one question may come, when is the trimeter complement invariant, right? When is the trimeter of a graph equal to the trimeter of its complement? So here is a nice theorem in this direction. So when it happens, and of course when both, then 6, 7, 8, these are the possible values. There can be no other values. And I will just briefly discuss the proof sketch. And so first we have to use a very standard technique from graph theory known as the Nordus-Gardum bounds to restrict the possible values of the trimeter from the huge set of natural numbers. And then we have to eliminate particular values, as you see over here, 3, 4, and 9 using some techniques. And the case of 3 is the easiest over here. And for removing the value of 5, we have to use a technique which is known as graph isomorphism, which is a very much an open problem in graph theory. So yeah, this is a theorem. And next, we come to graph coloring. So a chromatic number of a graph is defined as the smallest number of colors we need to color the vertices. So there's no two adjacent vertices. Adjacent vertices means that if they are attached by an edge, share the same color. And an example of graph coloring is shown by me over here. And this example is a very famous graph. It's called a Peterson graph, basically. And the minimum number of colors required is a chromatic number. And for any connected graph on n vertices, we have this very nice result. The chromatic number is upper bounded by this quantity, which can be described in terms of number of vertices and the diameter of the graph. And using the previous relation and using this particular inequality, I have reduced some results, which basically give us the chromatic number of a graph G given its trimeter is X. So we can find the upper bound on this particular chromatic number of the graph in terms of the number of vertices present in the graph, using the relation between diameter and trimeter and the upper bound of the chromatic number. And these bounds are quite sharp as well. Yeah. So now we shift our attention to something else and very interesting. So the figure you see over here is a strongly regular graph, and these were introduced by Rajchandra Bose, a very famous Indian statistician in 1953. They are a very special family of graphs which can be characterized by the number of vertices, edges, and lambda and mu, where lambda is the number such that two adjacent vertices, those two vertices as well with the edges. And every two non-adjacent vertices have exactly mu common neighbors. And as you can see, the diameter of this particular graph is 2, and this is widely used in combinatorics and many fields. And the trimeter of this graph obeys a very nice formula, which can be stated as follows. Yeah, so this is a theorem. So given a connected strongly regular graph, then the trimeter of the graph is 5 if G complement is triangle free, meaning that if we take the complement of this graph and if there are no triangles present over there, then the trimeter of this graph will be 5. We can tell that. And if it does not happen, then the value of the trimeter is 6. And the proof sketch is a bit complicated. So as I previously told, the diameter of this particular graph is 2, and and we can of course deduce an upper bound of on the trimeter by using the previously mentioned relations. And a strong result which is used over here is that if G is given in terms of n, k, lambda, and nu, then G complement is given in terms of n, n minus k, and all these things. Yeah. And then the proof further proceeds by taking two non-adjacent vertices of G, and then we have to carry out some particular calculations. All right. So now we come to the most interesting portion of the talk. Like if you open any particular mathematics resource on the internet, like the Wikipedia, or most famous, or the Math Wolfram, then you will get the value of diameter and radius of almost all graphs, because they are famous and they are known for the last 200 and 300 years. But what about trimeter? They were introduced just 3 years back, and someone needs to build a repository of them by finding out the values. So what I basically did is that I gratefully acknowledged the list of named graphs on Wikipedia, on which I took every graph, computed the trimeter of it by hand, and just made a collection. I did many of them. I will display just a few. Over here, we see one graph, we see another graph, and we see another graph as well. And yeah, so, and another very important thing which I wanted to mention in this aspect is that though I have used by hand, there is a very famous software known as Sage, which is extensively used in discrete mathematics and algebraic combinatorics to do this particular calculation relating to graphs. So yeah, you can see that computer science is having a bridge with mathematics. And yeah, so I would finally like to end by stating some open problems. So my current work and work in progress is in the direction of finding some more examples of graphs where the trimeter of the graph and the trimeter of a complement are same. So these were a few examples which were found by me and my guide, and we are trying to find more and trying to find some other properties of these particular graphs. And another very important thing which are working on it is the effect of removal of vertex and edge on the graph. Like if consider this particular graph, if we remove a vertex, what will happen to the trimeter? Will it increase or decrease? If yes, then how? And if we remove the edge, what will happen? So we cannot basically say anything about this. We are fairly open. We are trying to come up with some formulas regulating that. And yeah. So I basically come to the end of our talk. I would like to end on a light note. So as I had previously mentioned, a tree is a graph which does not have any cycle, but over here you see that a cycle has been forced into a tree. And yeah, so graph theory is in a bit problem over here. With that, I come to the end of my presentation. Thank you so much for your attention, and I will be very happy to answer questions. Thank you.
Okay. Thank you, Matthew. Matthew, would you like to tell me one thing? How come graph isomorphism is ruling out the possibility for trace to be 5?
Yes, sir. Very good question. Actually, the graph isomorphism comes into play because, and this is the thing which I'm going to tell, does not only apply for graphs, it applies for another very famous mathematical object known as groups, which I think everybody of here has heard. So what we do in proving this kind of quantities, we cannot actually consider all possible graphs in the world. They are infinite in number. What we do, we work out for a certain family of graphs and tell that these families of graphs are related to many other families of graphs by some way, by some transformation. And they are related in such a way that the properties of this family and the family of other graphs do not change. So we try to reduce our work in some sense. Reduce our work and consider just a small family such that they will be true for all other graphs. And this family is obeying the trimeter 5. So that's why we can use isomorphism. But one major problem in this direction is that it is very tough to check whether two graphs are isomorphic or not. And that's what I was telling in my talk, that it's still a wide open question.
So means the set of the group that you are going to form, that's going to have the trimeter to be 5 in the that you are finding.
Yes.
Okay.
Means so I will take any particular graph with trimeter 5 and I will show that it does not hold. That it becomes isomorphic to some particular kind of graph where the trimeter of G will not be equal to the trimeter of G complement, and then I will be done.
Okay, in the physical sciences and all the physical sciences subjects like science, physics, chemistry, biology, we do use the graph theory. So can you try to give any physical example where we practically use the graph theory, either from chemistry or physics?
Yes,
some simple so everyone can understand.
Yes. So I will like to mention two examples. One is from chemistry, and another, I will not say totally physics. It is related to physics, biology, and everything as well. So first of all, in chemistry, there is a very, very beautiful subject known as Combinatorial Chemistry. So I came to know about it last year while I was taking a computational chemistry course. So there, as far as I know, I do not know much in details. So as you can imagine, the graphs contain a certain kind of quantity. So in the computational combinatorial chemistry, they are taken as atoms, and the edges are taken as bonds, and then their properties are studied. Yeah, so that's a very interesting kind of area, and much work has been done on that. And their folding of them, their various configurations, and these kind of things are studied. And in physics, there is a subject which is known as sociophysics. So in sociophysics, basically, So, and very good example is when an election happens. Let's say the Lok Sabha election. So it happens all around India. So people try to predict what will be the outcome. And over there, citizens are taken as vertices, and two citizens are joined if they have the same political opinion. And by that, and they are actually, yeah. So by that, we can construct a model for the social networks, and using that and another concept known as random graphs, where the vertices do not remain fixed, we can tell a lot number of possibilities, and many political specialists do use these things, and this is a new
Okay.
subject in social physics. Yeah.
Okay, Matthew. Beyond social physics, I was. It would have been better if, like, molecular dynamics, we do use
Yes, sir.
the.
Like in molecular dynamics, those concepts come under computational combinatorial chemistry more. Yeah.
Okay. Thank you, Matthew.
Yeah. Thank you so much.
So in this, you are talking about radius of a graph and diameter of a graph. So what are these quantities?
The radius of a graph is defined as the minimum of the vertex set. So as I mentioned that the eccentricity is defined as the maximum of distance between two particular vertices. And if we construct the set, the minimum of this is defined as the radius, and the maximum of that is defined as the diameter.
So in what case can they be equal?
One trivial example is in the case of an empty graph, but that will be much more trivial if you take complete graph. Yeah, so the complete graph, I mean that if we are given a certain number of vertices and every possible vertices is joined by edges, in that case they are equal.
All right.
And in graph theory, basically, the thing that they are equal, this is known by a very mathematical term. It is known as type. So if if we can demonstrate any example where these things become equal, we say that this inequality is type. So this is just a term.
All right. Thank you.
Type bound.
Okay. So, Matthew, I have a question. Like, you talked about the chromatic number. So
Yes.
that you said that minimum number of colors, so that two adjacent sides should they don't have the same. Yeah, two
Yeah.
adjacent vertices don't have the same. So, like, if like we have a circle and we say like we make it we divide that into like some points. Suppose so, like that circle can be like it's made up of so many points. So, like, can we define the chromatic number of a circle?
Yeah, actually, what you talked about here is that, so, ma'am, you can look up one thing in the internet. So, it is not only generally valid for a circle. You will be amazed to know that it is valid for the entire plane. So, in graph theory, there is a very famous and very difficult open problem known as the Hadwinger-Nelson problem. I'm not going to the details of what the problem is, but it in somehow concerns about the chromatic number of the entire plane, of the entire 2D plane. And it tells that you can always find 2 points of the same color being separated by one distance and so on and so forth. But yeah, so it is very difficult to define the chromatic number, and that is what mathematicians and more specifically combinatorialists have been doing for the last few decades. They have been trying to define the chromatic number for circles and so on figures, such as they can prove the conjecture or disprove the conjecture. So I cannot give any definite answer of how they can be defined, like the way of a graph. But yeah, they are difficult, and work is still being going on, so that they can be defined on that.
So,
And
can we just like treat circle to be like made up of so many points, and like so we need like so according to me, I think like either we need two colors or in some cases we can need three colors.
actually, yeah. So in that way we can do, but and the main problem which comes into the play is that, as you very correctly mentioned in the beginning, circle consists of many points, and many here means infinite, and that means
Yeah.
continuous. But the entire picture about what I was talking is discrete. So
Yeah.
like 1, 2, 3, like this, and in continuous we get 1, 1.2, 1.111112, and all these things. So the like we cannot have an exactly similar picture like that of a graph, and problems coming to the play. And that's why the Hadwinger-Nelson problem is still widely open. So this is one of the main reasons. So if we color like that, some by like we can of course, but some violation of rules do happen. That's why it does not. It becomes ambiguous.
Okay, so one more thing, like
Yes.
you talked about the minimum distance somewhere, like
Yes. Yes.
in the
Yeah.
beginning, yeah. So, like, do you know like what is geodesic?
Um, yeah, so actually, I was doing a reading project on hyperbolic geometry, so I have very little understanding. But geodesic, as far as I know, is that if we consider any particular surface and if we consider arbitrary 2 points, the geodesic is the shortest distance connecting the 2 points or something like the great circle or anything. Yeah.
Yeah, that's the shortest part. So, do you know the geodesic on the surface of a cylinder? Like, if we have 2 points on the surface of the cylinder, what is the shortest path joining the 2 points? Do you know that?
If we take no, ma'am, actually, I have no idea about this.
Okay, it's basically it's helix. So you can read about it.
Yeah. Okay, okay.
Oh, thank you.
Yeah, thank you so much, ma'am.
Hi. So my question is, you
Yes.
define diameter. So I want to add like both the benefiting of defined diameter on application wise, because we already have a Vogel approximation and for the transportation problem and Hungarian method and all. So is it really solve some problem by defining diameter, or is it just yet a abstract definition?
Actually, as far as I know, it is like the origin of trimeter is abstract. Like the main study came out of a similar quantity which was being studied for something, some other problem. But yeah, so applications may include like I do not know any very famous theory or problem where this can be applied. But recently, I was doing one particular small kind of problem, so they can be used to solve some small problems in graph theory. And so till now, I am not aware of a very huge application, but I think in future it's possible. So like it can be extended to the world of random graphs where the radius and diameter are well studied, but the trimeter has not been introduced that much. And I have not still now studied random graphs much, but I plan to do that in the future. So there, and in random graphs or in network theory, they can come into the picture and they can be of some help, like reducing some complexity in some problems, or let's say, yeah, so reducing the cost or something. It might happen. We never know.
Okay, and my second question is, you say that in future you are working on when the diameter is equal to the complement of the graph.
Mm-hmm.
So basically, what does this mean physically? Like, if the diameter of a graph is equal to its complement, then what this mean physically? How can I see this thing?
Actually, like in many concepts in graph theory, so the main principle in graph theory is that we get a lot of bounds and inequalities and equalities, but the physical meaning of this is very tough to define. I will accept that. Of course, it's tough, but yeah. So if we can find out some more examples, like if we can construct some more examples, those graphs may have some peculiarly difficult property. Like I told that a work is in progress. The very reason is that I have tried hundreds of small examples, but none have fit. But I have not been able to prove that we can never construct a graph with, let's say, 200 vertices that this trimeter is, sorry, not 200 vertices. Yeah. So this, yeah, when any other configuration that this trimeter of the graph and the complement will not be equal. So in physical application, I don't think is much in graph theory per se, but in other other subjects which are aligned to graph theory, like network theory or subjects in biology and neuroscience, there can be some applications.
Okay, like the flowing problem, infinite flowing problem, you can see.
Yes, yeah.
Okay, and my last question is, you talk about vertex currying. So the vertex currying,
So can you please repeat?
vertex currying. You say about the vertex currying.
Vertex align. Yes,
Yeah.
yeah.
So there is a concept in it, Yatin square. So do you know what is Yatin square?
So what can you please
Yatin
repeat?
square. AATIN.
Y A
AATIN. Yatin square.
A T I N A T I N
Any A. AA.
18.
Let me
ATI
write
and
it.
Z.
Let me write it. It's in the chat box.
Yes, that will be the best, I think.
So do you know what it is?
Latin square. Yeah, I think I have heard about this, and there were some problems which were framed by Euler. Am I going in the right direction? I think yes.
Yeah.
I've of course heard
Yeah,
about
yeah.
this, but I have not studied this. These were formed by Euler, and they were some disproved by someone. So Euler spoiler that concept came. Shrikant, Indian
There is something
mathematician.
like chromatic polynomial in this topic.
Yes, of course. In graph
So-
theory, there is chromatic polynomial. Yeah,
So what is
I have not
chromatic
discussed
polynomial?
them.
What is chromatic polynomial?
Yeah. So in chromatic polynomial, so we have to construct the adjacency vertex of the graph, and then take the characteristic polynomial, and yeah. So then I think we can get it.
Okay, fine.
I think that is the end of questions. Thank you, Maitreya. We'll be moving on to the next participants. Is the next group that comprises of Saurabh Chakrabarti, Sanjana Malik, and Sayani. Are you there? If any of the group members are there, you can respond so we can acknowledge your presence. Okay, then the next group, the presentation after that is by Komal Prajapat. I think even she's not here. Since the next two presentations are not here, we conclude with the session for today.
Okay,
And
Veer, are you going to check with them or are we concluding?
So we will check with them, but we haven't got any response. So if we can, we will try and put them in a slot tomorrow.
Okay, tomorrow I think it will not be possible because we have a very tight schedule.
Yes, sir, but there's no response from these participants. So now we don't have an option but to conclude, sir.
Okay, then. That's good.
Okay, so with that, we conclude the second day of the Meera Memorial Paper Presentation Competition 2022. It was a pleasure having all of you present, and we will see you again tomorrow for the last day, for the third day of the competition. Thank you so much. Thank you, judges, for coming, and thank you so much for everybody else who joined us today.
Thank you, everyone.
Thank you all.
Thank you.
Thank you, everyone.